For the longest time, the world of computer chips was, well, it was simple. But those days, they're long gone. A totally new, much more complicated war for chip supremacy has kicked off. And today, we're going to take you right inside the battlefield.
So you might be asking, why the sudden change? I mean, for decades, the game plan was easy, right? Just make the transistors smaller, cram more of them on a chip, and boom, everything gets faster. We all knew it as Moore's Law. But that whole era is over. It's done. And now, chip designers are facing these brutal choices they never, ever had to make before.
Okay, so to really get what's happening now, we've got to look back. Before this war, there was, well, you could call it a long peace. It was an age of predictable, almost guaranteed progress that literally built the digital world as we know it. Yeah, for something like 50 years, the industry was basically on cruise control. You had Moore's Law, which promised that chips would get twice as powerful about every 2 years. And then you had this other incredible thing called Dennard scaling, which meant they could do all that without getting hotter. It was literally a free lunch. You got more power for free. But then, around 2015, the laws of physics just caught up. We could still make the transistors smaller, sure, but they stopped getting more power efficient. And just like that, the free lunch was officially over. So here's the key takeaway, right? The old playbook got thrown out the window. A totally new one had to be written from scratch. Chip designers can't just win everywhere at once anymore. They have to pick their battles, make some really tough trade-offs. And this new war, it's being fought on 3 main fronts: data, power, and specificity. All right, let's dive into the first battlefront. And here, the enemy isn't how fast your processor is. It's how starved it is for data. I mean, think about it. You can have the most powerful engine on the planet, but what good is it if you can't get any fuel into it? It's completely useless. And this problem, it has a name. It's called the memory wall. See, our processors have become ridiculously fast, but our ability to feed them data from memory, from RAM, it just hasn't kept up. It's the ultimate bottleneck. It's exactly like having a Ferrari engine, but you can only refuel it through a tiny little coffee stirrer. So performance isn't just about how fast you can crunch the numbers anymore. It's about how fast you can feed the beast. And this quote from Chips and Cheese just nails the core problem. A modern chip isn't one thing. It's a whole system. You've got the CPU, which is like a picky eater. It wants a lot of memory capacity, but it's not super sensitive to the speed. Then you've got the GPU, and it's the total opposite. It's just ravenous, absolutely thirsty for data. It needs a massive fire hose delivering hundreds of gigabytes every single second. Trying to keep both of those parts happy at the same time, that's the real challenge. So how did Apple try to solve this? Well, their approach was pretty radical. Instead of having separate pools of memory for the CPU and the GPU, they just said, forget that. They put one giant, super fast pool of unified memory right there on the chip package and made it accessible to everything. And what you're seeing here in this table, from the M1 all the way up to the M1 Ultra, that is a straight-up brute force assault on the memory wall, and it absolutely changed the game for what a laptop was capable of. Okay, so winning the data battle is awesome, but can you do it without literally melting the chip or draining your battery in like 5 minutes? And that question, that brings us to the second major front in this new chip war. This is what we call the power wall. It's pretty simple, really. Every single calculation a chip makes generates a tiny bit of heat. Now, multiply that by billions of transistors all firing off at once, and suddenly that heat becomes a massive physical barrier. You can't just keep making the chip faster and faster, because it'll just get too hot to even work. So the battle shifts. It becomes all about efficiency. How much bang can you get for your buck? Or, in this case, how much performance can you squeeze out of every single watt of power you use? And this chart really shows you just how wide the battlefield is. I mean, on one end of the spectrum, you have a tiny little processor for an Internet of Things device. It's designed to sip nanowatts of power so it can last for years on a coin cell battery. Then, on the complete other end, you have a monster AI accelerator in a data center that's guzzling 1,000 watts. That's enough to power a microwave oven, all for raw performance. So you can see, engineers are fighting this power war at every single scale imaginable. And this is another place where Apple's strategy was a total game changer. They use this clever mix of what they call high-performance cores and high-efficiency cores. The chip intelligently sends tasks to the right core for the job. The result? A huge leap in what we call performance per watt. This chart is showing you G-flops. That's billions of calculations per single watt of power. This is the secret sauce. This is how they manage to deliver professional-level performance in a laptop that's super thin and light. Okay, so we've tackled the battle for data, and we've tackled the battle for power. The third front in this war really opened up when the industry realized something crucial. Trying to do everything with just one general-purpose tool just wasn't cutting it anymore. And that realization led to the rise of what we call domain-specific architectures, or DSAs. The whole idea is actually super simple. For some jobs, a specialized tool will always beat a general-purpose one. You know, a Swiss Army knife is useful, but if you need to build a house, you're going to want a hammer, a saw, and a drill. The exact same thing is true for silicon. So what we've seen is this great divergence in chip design. We still have the CPU, right? That's our reliable jack of all trades. But sitting right next to it now, we have the GPU, which is an absolute beast at parallel processing. And then you have these hyper-specialized units like Google's TPU, which is designed from the ground up to do one thing and one thing only: run AI models at absolutely breakneck speeds. So what's the TPU's secret weapon? It's something called a systolic array. Now, the best way to picture it is like a massive two-dimensional grid of really simple calculators. Instead of fetching data one piece at a time, data just gets pumped through this grid in these perfectly timed, efficient waves. This allows it to do the massive matrix math that's at the very heart of all modern AI with just incredible speed. It's the definition of a hyper-specialized tool, and it's what gives the TPU its insane performance edge. So, okay, we've got our three battlefields: data, power, and specificity. The battle lines are drawn. So the big question is, where does this fight go from here? What's the next frontier in this war? Well, some companies are just deciding to rethink the entire battlefield. Take a look at this. This is the Cerebras wafer scale engine. They looked at a normal small computer chip and said, that's not big enough. So instead, they built a processor on an entire silicon wafer. We're talking an astronomical 4 trillion transistors. The whole idea is to completely eliminate those communication bottlenecks by just putting everything on one single giant monster of a chip. But there's a catch. As these chips get more and more complex, cramming CPUs, GPUs, AI accelerators, unified memory, all onto one system on a chip, they start to create these new, really unexpected weaknesses. It turns out that the very solutions we're creating to solve our performance problems might be opening the door to brand new security problems. And this is the new reality we're living in. Look, Apple's M1 chip was an absolute triumph of engineering, no doubt. But its very complexity introduced these subtle new flaws. Researchers discovered that apps that were supposed to be completely sandboxed and isolated could actually find ways to secretly pass data back and forth. In some cases, they could even spy on what was happening on your screen just by monitoring the traffic in shared parts of the chip. It's the ultimate trade-off. In solving the performance problem, you can accidentally create a security problem. And that really brings us to the ultimate takeaway here. For decades, we thought of hardware as just a general platform that could run any software you threw at it. But this new war for chip supremacy, it's flipping that entire idea on its head. This specialized, incredibly complex hardware being designed on these battlefields today is now defining the absolute limits and the incredible new possibilities of the software of tomorrow. The silicon isn't just the foundation anymore. Now it's leading the charge.